Imagine waking up tomorrow to find that a core global financial network has been entirely compromised. I'm talking ledgers completely wiped out, data permanently altered, and trust completely shattered, all simply because the underlying foundation was brittle enough to crack under pressure. The stakes of our digital infrastructure failing are, frankly, catastrophic. But what if we could make that kind of failure physically impossible? Welcome to this deep dive explainer where we are meticulously unpacking the mathematical code that guarantees system survival against adversaries. Today, we are looking at something truly extraordinary. We aren't just talking about abstract theories or high-level whiteboard concepts for building better networks. No, we are examining literal, formalized mathematical proofs, specifically written in the lean programming language that mathematically enforce anti-fragility. We're going to go incredibly in-depth today to truly understand the architectural blueprints of systems that don't just resist attacks, but are mathematically barred from failing under them. Okay, so let's dive right into this foundational question. The lean theorem code we are looking at today attempts to provide the literal God formula for an unbreakable system. Think about the legacy networks we rely on every single day. They're essentially built on trust and reactive security, right? It's an endless game of whack-a-mole, patching holes as they appear. But what if you could write rules at the fundamental physics layer of a digital system that made breaking it logically impossible? How do you construct a digital fortress where a successful attack would literally violate the laws of mathematics? That is the bold, massive promise of what we are unpacking. Here is how we're breaking this down today. 1. Foundations of anti-fragile systems. 2. Latency and ledgermorphism. 3. Rules of quorum consistency. 4. Navigating and sifting semantic space. And finally, 5. Syzygy and Wallace bounding. Before we get into the heavy logic, it's absolutely crucial we define exactly what we mean when we talk about anti-theory and these rigorous mathematical constraints. Anti-fragile mathematics uses logic proofs to enforce behavior. In traditional software, you know the drill. You write the code and then run endless, exhausting tests to see if a hacker can break it. In formal verification with tools like Lean, it's totally different. You write mathematical proofs that a certain failure state cannot even exist in reality. The code simply won't compile if the logic isn't absolute. We are looking at a system built entirely on these undeniable, airtight guarantees. Section 1. Foundations of Anti-Fragile Systems. We are analyzing 8 specific Lean modules generated to define anti-fragility concepts. Now remember, these aren't just text documents or standard scripts. These are compiled theorem files. From anomaly cancellation all the way to Wallace bounding, these 8 pillars represent a complete overhaul of how we approach system architecture. They cover everything from basic network latency to the very preservation of meaning in human language. Digging into the foundational logic of the contrarian Byzantine latency feature, we find the exact definition for mathematical stabilization. In distributed systems, Byzantine actors, essentially malicious nodes or adversaries, often try to exploit the time it takes for messages to travel, which is known as latency. It's a classic attack vector. If an attacker can manipulate lag, they can manipulate truth. But this theorem defines an unbreakable mathematical relationship between a network, its latency, and its overall stability that cuts that attack vector off completely. There's literally no way around it. So the crucial point mathematically mapped here is a hard constraint of 10. Stability always equals latency plus 10. This isn't an arbitrary guess. It is a structural constant, deeply encoded into the system. Let's make this concrete for a second. Imagine a massive botnet floods a bank's server with fake traffic, driving latency through the roof in an attempt to crash the transaction ledger. Under these specific rules, no matter what the latency of a given network node actually becomes, the system's structural stability is formally defined as that exact latency metric, plus an absolute margin of 10. By isolating this hard constraint, the theorem guarantees that network latency will never outpace the system's structural stability. Because stability dynamically locks itself 10 points ahead of latency, the proof forces an absolute conclusion. Latency is strictly less than stability. This is massive in the real world. It means you have baseline anti-fragility. No matter how much lag an attacker artificially injects into a payment network or a decentralized system, the stability threshold automatically, mathematically, scales to safely contain it. The attacker can never catch up to the system's stability bounds. Section 2. Latency and ledgermorphism. Moving from basic stability into abstract physics, we encounter an algebraic, dimensionless ledgermorphism, where lag is simply an abstract counter of logical ticks or rounds. We aren't talking about hardware clocks or milliseconds here, because hardware can easily be spoofed by bad actors, and the speed of light varies based on physical distance across the globe. Instead, the theorem uses pure natural number counters. Think of this like a metronome ticking in a vacuum. It doesn't care about the real-world speed of sound or how fast a physical processor is spinning. It only cares about its internal, uncorrupted logical beat. This brilliantly detaches the system's logic from physical time, creating a dimensionless algebraic structure where latency is just a clean, unhackable measurement of logical events. Let's compare a low-lag regime against an overshoot regime to understand exactly how this handles an attack. The system operates on a two-regime spine based on a parameter called R, which represents the maximum rejection phase. In an honest low-lag environment, like normal everyday internet traffic, the abstract lag translates perfectly into the system's vent mechanism. If there's zero lag, you get a completely strong ledger. But what happens under a massive denial-of-service attack? An overshoot, where lag wildly exceeds R. The system does not crash, it simply saturates the vent exactly at R, mathematically dropping to a defined floor weight of 1. It survives by gracefully degrading to a completely safe baseline, rather than breaking under the pressure. This clamping function acts as a definitive hard boundary, preventing abstract network lag from exceeding that maximum rejection phase. By taking the minimum of the current lag and the maximum boundary R, the system forcibly clamps adversarial delays. An attacker could literally throw infinite abstract lag at this ledger, and the math simply ignores everything past R. This is true anti-fragility in action. The impact of an unbounded attack is strictly provably bounded by mathematical definition. Section 3. Rules of quorum consistency. Now we have to understand how a distributed system maintains absolute logical truth across its nodes. The parameters here establish committed reads and monotonic acknowledgements. In a distributed quorum, like a global network of servers trying to agree on your account balance, you often have nodes temporarily holding slightly different versions of data. The theorem solves the classic Byzantine generals problem by applying strict inequalities. It ensures that the value the system officially reads is exactly the value that was acknowledged across the network, leaving literally zero room for ambiguity or state corruption. Sequentially unpacking the logic of the proof, we see it takes 3 specific, unyielding steps to guarantee absolute data accuracy. First, it verifies that at least one node in the group has recorded the acknowledgement. Second, it rigorously checks that absolutely no node has recorded a future state. No one is allowed to be ahead of the current reality. By proving both of those conditions, step 3 is an undeniable mathematical conclusion. The overall read value must equal the acknowledged version. The system forces unshakable consensus through pure logical antisymmetry. To put it simply, these logical constraints mathematically prevent the system from ever traveling backward in its own state history. The theorems explicitly prove that a read version must be greater than or equal to a write version. That means you will always see the exact data you just saved, not some ghost of the past. They ensure monotonicity, which is just a formal way of saying time only moves forward. If a malicious node tries to inject a read that claims an older state than your first read, like trying to reverse a completed bank transfer, the math immediately flags it as breaking the boundary. It mathematically outlaws the very concept of dropping data or reverting to a vulnerable previous state. Section 4. Navigating and sifting semantic spits. We pivot now from network consistency into meaning preservation. The number 5 is critical here. It represents the 5 positions in the semantic space mapped by a highly advanced mechanism called the grasshopper cipher trajectory. We are now actually applying anti-fragile mathematics to language and meaning itself. When we communicate, words exist in a vast space of meaning. The grasshopper cipher uses a specific trajectory to navigate a 5-position semantic circle. The goal is to ensure that when meaning is processed or transmitted across a network, it doesn't get lost in translation or trapped in a meaningless loop. Think of an eddy in a river, trapping water in a redundant, swirling loop that goes absolutely nowhere. Aperiodic rotation prevents this exact phenomenon in data, ensuring a full harmonic cycle that maximizes semantic density. In language processing, a semantic eddy is a loop of stagnation. It's when communication repeats a state before fully expressing an idea. The math solves this using aperiodic rotation, by rotating through the space using steps that share no common divisors with the total space. Like stepping by 3s in a space of 5, the system mathematically guarantees it will visit every single unique position before ever returning to the start. It enforces a complete, dense cycle of information without any redundant loops. Furthermore, this semantic sieve mathematically measures word embedding variance to differentiate between rich, multiple valid meanings and destructive ambiguity. Let's explore polysemy, words with multiple meanings, like the word bank, a financial bank versus a riverbank. The proof dictates that if an embedding length is greater than 20, the system successfully extracts 2 standing waves. In physics, standing waves represent stable concurrent frequencies. Here, it means the system successfully holds two valid, parallel truths, recognizing rich metaphor. But if the context length is 20 or less, it results in zero modes. It mathematically proves the signal is just ambiguous, destructive phase opposition, where meanings cancel each other out into static. It is literally an automated, uncrackable filter for clarity.
Section 5. Syzygy and Wallace bounding.
We've reached the apex of this architecture. The Syzygy and Wallace theorems govern the absolute capacity of the system. They prove that there are physical, or rather mathematical limits to how operations can scale, and incredibly, how components can pair together to unlock efficiencies that simply shouldn't exist linearly. Notice that the true ground state is mathematically proven to be anti-parallel, utterly distinct from parallel or orthogonal relations. In these modules, the term syzygy is defined as the perfect alignment of components. But here is the magnificent irony of the math. To achieve perfect alignment, the components must be anti-parallel. They have opposite functions, opposite spin pairings, yet they share the exact same pipeline. The theorem formally proves that this specific anti-parallel clash is actually the absolute ground state of maximum efficiency. This brilliantly illustrates how specific architectural layouts leverage this exact syzygy to generate a throughput that mathematically blows past the capabilities of individual, unaligned components. The lean proof explicitly calculates this. A pipeline throughput of 2 and 4 equals 8. The theorem goes out of its way to prove that 8 is vastly greater than the simple addition of isolated components. It mathematically proves that when anti-parallel components align in syzygy, the system experiences a profound compounding effect. You don't just add their power, you multiply it. You create a system that is fundamentally, provably greater than the sum of its parts.
Let's look at the final proof, the Wallace bound. It systematically ensures that the actual frontier area of any system operation can never exceed its mathematically defined absolute envelope. Think of the envelope area like a mathematically unbreakable speed limit for a global processor. The code defines the highest point of activity, the peak frontier, among any operational branches. It then draws an absolute envelope based on that peak. The proof strictly mandates that the actual processing sum of those components can never, under any circumstance, break past that mathematical limit. The system's growth and load are perpetually and provably contained. It literally cannot overheat.
Leaving you with that thought, if the God formula for anti-fragility exists as an undeniable mathematical proof, it fundamentally rewrites the baseline for how we must build all future networks. We've just seen how malicious latency can be effortlessly outpaced by structural stability, how abstract ledgers can gracefully handle infinite lag, how human meaning can be preserved through aperiodic rotation, and how system alignment multiplies power while strictly bounding risk. The math is here, and it is absolute. So what fragile structures in our world are already obsolete? Thanks for joining me on this deep dive into the blueprint of unbreakable systems. Keep exploring, and I'll catch you in the next explainer.